Hey everyone, good afternoon and welcome to APSC 174 Midterm 2. So we are going to begin in 30 seconds officially to give everybody the time to get here at 1. As I'm sure you know already, my name is Antoine and my email is antoine@prep101.com. So if you want to share any documents with me, if you want to email me any questions, if you want, to talk to me, of course, in the session, you can use the Q&A, but that is my email that I encourage you to use for questions, for comments, for anything. I'll make my introduction short. I am a tenured professor. I've been teaching since 2000, and I've been with CourseCram since 2005. So I've taught, I don't know how many sessions, a lot of sessions, like on hand with CourseCram, there's like 400-ish sessions, but I also taught with companies that are friends with CourseCram. I taught my own sessions. I've done like 1 million private tutoring hours. So you are in very, very safe hands. I do this for a living, as we say. Today's focus will be our midterm 2 for APSC 174. I went ahead and I wrote down the topics from your weeks. I think 6 to 11 or week 5. I forgot what the week numbers are, but I wrote that down. We're going to cover these. My approach will be, as usual, in a problem-based approach. I will explain the theory to you briefly. I mean, maybe sometimes not so briefly, because there's some theoretical bits here that I really need you to understand, but definitely not like a classroom where we're going to spend an hour and a half discussing theoretical stuff. So I'm going to present the theory. I'm going to tell you what it says. I'm going to tell you how to apply it, and the focus will be how to solve problem to be able to solve whatever problems that shows up on your midterm. In preparation for this, I gave you already, it's posted on the website, all older midterms, because I know they post for you 2019, 2021, and 2022. Those you have, and you have their solutions and everything. I posted for you earlier midterms. I think I posted 2016 to 2018. So that gives you a lot of questions to practice. That gives you a lot of midterms that you could look at for practice. I'm going to do that also. And in preparation for the session today, I also broke down the 2019 to 2022 midterm based on topics. So for example, I took out all the problems that have span, linear independence, dimension, whatever, and I put them in one document. So these are the ones from 2022, these are the ones from 2021, and so on. If you've taken any sessions with me by now, you know how I do this. I break down the midterms by topic rather than by year, so we could just practice per topic, not per year. We're going to solve many of those. If you have a particular question from somewhere else, if you have anything that troubles you, again, if you don't know me, then I'm sure you know someone who knows me. You know I'm here for you. My sessions are 100% dynamic, so I will adjust to you that rather than ask you to adjust to me. This is a recorded session. Recordings will be available tomorrow, and the notes will be available also tomorrow at 4 p.m. Everything I write, everything I draw, everything I will put in here will be ready for you on the course page tomorrow at 4 p.m. If you have any concerns, any questions in the session, please use the Q&A. I said this many times. I love teaching Queen's sessions because you guys are vocal, you talk, you say things, you say, I get it, I don't get it. I hope this is as usual kind of Queen's session where we're going to talk. You're going to tell me you understand, you don't understand. I will do my utmost to help you ace the midterm 2, and then again after that for the final. I hope you did well on your APSC 172. I know there's a lot of crossover between the two courses, so I hope that was good. I hope you did well on your midterm. and I look forward to working on both finals of these courses. I hope I didn't. Last thing, sometimes people ask me about printed material. In my sessions, there are no printed material because I basically don't use them. So there is a course booklet. There are some problems and some solutions there, and they're posted free on the course page, but they're basically extra to what we're going to work on right now. This is how I've been doing it for Queens for a long time. It's a formula that has worked. People usually do well on their tests and midterms and finals. So why change a winning formula? The one thing I'm not sure about, and I couldn't get the answer from your notes, I didn't see it in your teacher's notes. So I'm not sure if you have a different set of notes that they give you or whatnot. Do you have to find the basis of the image space? I know you need to know what an image space is, and you need to know what the kernel is and all that, but do you need to find the basis for the image space and the basis of the kernel? That's one thing I wasn't able to get an answer on from the notes. So if you could at some point answer me this, that would be great. Anyway, it's I probably will do it tomorrow. So you need to put the vectors in a matrix, reduce, and then get the vectors with leading ones to be the basis of the image space and so on. So let's assume that you do and aim to cover it then. It's covered in some years, it's not covered in some years. So I'm not really sure. Let's assume it is, and then we'll aim to cover it. It'll mean we have to work the other topics a little bit faster so we can get to it. Fair enough? I am beginning with the topics that have crossover from before. Well, thank you, guys. I'm going to begin with basis, generating set, coordinate, dimension. I'm doing this line of work, linear independence and dependence. As a first step. So let's begin. There's going to be some stuff that you know already from midterm 1, but I'm going to assume you don't. I mean, and go through it a little fast. I can't do it in as much details as we've done it for midterm 1, but I can certainly go over it really quickly. Please, my last comment is this: as usual, please, I tell all my other sessions, be like Queens, because Queens talks to me. So, you are Queens, so I can't tell you be like Queens, but just be Queens. So, tell me if you don't understand anything. Tell me if something's not clear, and I will clarify it for you. All right. Well, let's begin. Let's discuss the idea of a span and a generating set. So, what is a span? And what's the idea of a generating set? Look, whenever we say vectors, so the idea is this. So vectors v1, v2, all the way to, let's say, vk. We say that these vectors span Rn. These vectors span Rn, or we can say span Rn, or we can say are a generating set for Rn. So span Rn, that's another way of saying it is are a generating set for Rn. This means, so the meaning is, any vector in Rn can be written as a linear combination. You know what? It's the first time we use those words, so let's write them fully. Linear combination of those vectors v1 up to vk. Okay, what does it mean that a linear combination of v1 up to vk means? For, I'll say this in a different way, for any x in Rn, so you pick whatever vector x in Rn, x can be written as a1 v1 plus a2 v2 plus all the way AK, VK for some A1, A2 uptake. So you pick whatever vector you want in Rn, and you will be able to write it as a linear combination of those vectors V1 up to Vk. Let's pick a very silly example first. For example, the vectors 1, 0 and 0, 1, they span R2. They are a generating set for R2. I think you prefer generating set, so let me do that. They are a generating set for R2. Now, why is that? Because you pick any vector in R2. So you pick let xy, let's say, be any vector in R2. I am able to write xy as a linear combination of 1, 0 and 0, 1 in the most obvious way. You can write xy, now this is obvious, it's x times 1, 0 plus y times 0, 1. And this is for any x and y. Okay, that was kind of easy to see, right? Any vector xy is x times 1, 0 plus y times 0, 1. So let me give you another example built on this so we can establish a new idea. Now, 0, 1, 0, 0, 1, 1, 1, and minus 2, 3 is a generating set for R2. Yes? So this is a generating set. Why is this a generating set for R2? Well, because basically 1, 0 and 0, 1 already generate all of R2. Already these two vectors are a generating set for R2. So these two vectors can just sit and drink tea. I mean, they could just sit and do nothing, right? So already those two vectors are a generating set. So the other vectors can just do nothing. So one way to do it is you can say xy for any xy is x times 1, 0 plus y times 0, 1 plus, we don't need the other vectors, 0 times 1, 1 plus 0 times minus 2, 3. And here you go. I wrote any vector xy as a linear combination of these vectors. Now, of course, this is not unique in this case because there's way too many vectors, but we will talk about this in a bit later. What I'm trying to say is a generating set is kind of a loose concept. Like, if two vectors generate a space, then those two vectors with any other set of vectors can generate the same space. So I don't know. Let's say if me and Abby can build a bridge, then me and Abby and Andrew and Asher can build a bridge. The others can just sit down and watch us build the bridge. Do you understand what I'm saying? So if a bunch of vectors are generating sets, so you could just add things to the set and it'll still be a generating set. Okay, how am I going to express this theoretically? Remember this. In fact, I don't know if you remember this from before, but learn this or remember this. If the dimension of V is equal to n, that means you need a minimum of n vectors to be able to start talking about the generating set. So if the dimension of V is n and you have V1 all the way up to Vk is a generating set. So if we have a generating set, that means K must be bigger than or equal to n. So to generate a space of dimension n, you need at least n We're going to add later linearly independent vectors. So if a vector space has dimension n, to create a generating set for that vector space, you need at least n vectors. Do you get what I'm saying? Now, is it guaranteed that you have more, if you have more vectors than the dimension, is it guaranteed that you're going to get a generating set? Let me ask you this. Is 1 0 2 0 3 0 a generating set for R2? Well, R2, we know from before that the dimension of R2 is 2. And if we didn't know, then you should know this. Whenever you have Rn, the dimension is n. Of course, the dimension, we're going to study it in details later. For now, let's think of the dimension as the minimum number of vectors needed so we can start talking about generating a set. Do these vectors form a generating set for R2? Jamie. Hey, Jamie. I remember Jamie. And Jamie, Andrea. Well, the answer is definitely no. Good job, Evan. Evan is a confident no. Definitely, it's a huge no. Why? Because look, guys, I'm gonna give you a couple of reasons. Reason number one, I want you to look at these vectors. And aren't these three vectors, they're basically copies of 1 0? Aren't they all just basically copies of 1 0? Like it's 1 0, 2 0, 3 0. They're just the same copy of the same vector. So one of them is this, the other one is this, the other one is this, the other one is this. So you're just basically getting copies of 1 0. So that means they are basically, and I use the word basically very, very loosely, right? So they're basically one vector. There's not three vectors here. There's just one vector here, and then copies of that vector. So you need at least two like different vectors to generate R2. So that's one reason why the answer is obviously no. The second, which is a more kind of like a blue collar reason, like a counter example. Let me give you 1 2 in R2. So 1 2 is a vector in R2. Can you write it in their span? Can you write 1 2 as a combination of those vectors? And the answer is we really can't. How are we going to get 1 2 if the second component of all of these vectors are 0? But I mean, if you take 1 2 equals a times 1 0 plus b times 2 0 plus c times 3 0, this one would have no solution. I invite you to just simply look at the last row. 2 is equal to 0. That means 1 2, this means 1 2 does not belong to the span of the vectors 1 0 2 0 3 0. So that means those two vectors do not span R2. Okay, so what do we need to span a space? We need at least the same number as the dimension of the space, but even then it's not guaranteed. We need kind of two original vectors if the vector space has dimension 2. So we need two original vector, or you know this by now. You didn't join class yesterday, you joined it at the beginning of the term. We need two linearly, independent vectors. So the next step is to discuss what does it mean that vectors are linearly independent. So linear independence. And if you've looked at your midterms, you've seen past midterms, you know that this is a very, very important topic. So vectors v1, v2 up to vk are linearly independent in Rn. By the way, we can say that the vectors are linearly independent, or we can say that this is a linearly independent set in Rn. So whichever way you like to formulate it. So these vectors are linearly independent, or this set is of linearly independent vectors. This means, okay, in English, I'm going to tell you in English what it means, then we're going to talk about mathematically what it means. Not one of these vectors can be created using the other vectors. These vectors are truly original vectors. Not one vector is a linear combination of the other. So in English, this means not one vector is a linear combination of the other vectors. So every one of those vectors is independent of the other vectors. Every one of those vectors is just an original vector. Now, mathematically, this means that the only solution to A1 V1 plus A2 V2 plus all the way to AK VK is equal to 0. So if you form the system of equations, A1 times V1 plus A2 times V2 all the way till AN plus VN, then the only solution to this system is A1 equals to 0, A2 equals to 0, all the way till AK equals to 0. And what is this called? What's this solution called? This solution is called the trivial solution. The trivial solution, because it's the obvious solution that one thinks of when you look at this system. If I tell you, for example, A times X plus B times Y is 0, the obvious solution is A is 0, B is 0. Right? That's kind of the trivial solution. If you're setting something equal to 0, then the solution that's free to all of us is just when you set all constants equal to 0. This is why we call it the trivial solution. And that should be the only solution to our system. Okay, now here's a very important theorem that is kind of the sister of this theorem. Right, see here? So if you want, we can call this a theorem. So if we have a vector space of dimension n, and if we have a generating set, then we should have k bigger than or equal to n to be able to call it a generating set. Now, this theorem is about linear independence. So if we have V1, if V1 up to Vk is a linearly independent set in Rn. So if this is a linearly independent set in Rn, that means the number of vectors cannot exceed n. That means k must be less than or equal to n, which means you know that this space has dimension n. Okay, is a linearly independent section in V. Let's make this in general, and the dimension of V is n. Doesn't have to be Rn. It really could literally be any vector space. So if we have a set of vectors that is linearly independent in a space of dimension n, that means we cannot have more than n vectors. Okay, let me say it differently. When we say the dimension is n, that means this is the maximum number of linearly independent vectors in V. So when we say the dimension of V is n, that means in V, theorem, Andrea? THM, theorem. So if the dimension of a vector space is n, that means n is the maximum number of linearly independent vectors that you could have in this space. So more than n, that's automatically linearly dependent. Sometimes I like to say this, like it means V, if the dimension of V is n, that means V is a car or a bus that has n seats. So if people walk into it, there's n seats. If you bring in more than n vectors, some vectors have to be sitting on top of each other, so they're going to be dependent. So you cannot have more than n vectors in there and they would be independent. More than n vectors automatically means they are dependent. Fair enough? Let's talk about a few examples of this, and then I am going to go to your midterms. I'm going to solve some problems, but first, like, I need to establish some basic rules, some basic theorems, some basic knowledge, and then we're going to go and we're going to practice. So let me ask you this: is the set, let's do this, 1, 2, 3, 1, 0, 0, 1, 0, 1, and 0, 0, 1. Is this set linearly independent? Don't all answer me at the same time. Hi, Evan. Hi, Jamie, again. This vector is definitely not linearly independent. Why is this not linearly independent? Because these are 4 vectors in R3. Right? These are 4 vectors in R3. R3 is a space that has dimension 3. The dimension of R3 is 3, which means 3 is the maximum number of linearly independent vectors. So if you have more than 3, you are guaranteed that these vectors are dependent. There is a test to do in this, but just give me a second and I will tell you. First, I need you to understand the theoretical issues here. Now, let me ask you this. Now, what if I pick less than 3 vectors? Am I guaranteed independence? So is the set, let's say 1, 1, 1, 2, 2, 2 linearly independent? I mean, these are 2 vectors in R3. Am I guaranteed independence? Marth, it's 1, sorry, 1, 2, 3 components. Right? Every one of those vectors has how many components? 1, 2, 3 components. That's what makes it in R3. Thank you for your question. So, are these linearly independent? These vectors are in R3, so these are 2 vectors, and each one of those vectors is in R3. Are they linearly independent? Can you tell me why not? I mean, it's 2 vectors. Why are they not linearly independent? Well, because one of them is clearly a copy of the other, because the answer is no, because one vector is a multiple of the other, because one vector is a, well, you know, let's make it, because the vectors are parallel. That means one is a multiple of the other. And by the way, that's the case for two vectors. When you have two vectors, it's incredibly easy to decide whether they are linearly independent or not. Just with two vectors, it's very simple. If they're parallel, they're dependent. If they're not parallel, they're independent. So this, I'm going to write this as a note, and this is only for two vectors. So for, I'm going to write this big, for two, only two. For two vectors, if they are parallel, it means they are dependent. If they are not parallel, it means they are independent. That's the case for two vectors. It's very, very simple. It doesn't work for more than vectors. So to build on this example, if you say is the set 1, 2, 3, 1, 0, 1, is this linearly independent? The answer would be the answer would be 100%. Yes, they are not parallel, therefore they are linearly independent because those are just two vectors. Now, even if you wanted to prove it the long way, so these are two vectors. So not parallel means independent. Even if you wanted to prove it the long way, you could. So you can take, so A times the first vector plus B times the second vector equals to 0, 0, 0. This tells you that A plus B equals to 0. 2A is equal to 0, and then 3A plus B equals to 0. And when you solve this system, you will get A equals to 0 and B equals to 0. So this is the only solution. So this is the only solution, which means they are independent. Of course, this is or another solution. If you don't want to use the they are linearly independent, Z. Yes, they are. It's basically the same example as I just did, right? You can write down this and you can check that the only solution is A equals to 0 and B equals to 0, right? Those are definitely linearly independent. Basically just the same proof as we just did here. So how do we do a quick check for linear independence? Linear independence, a quick check, I don't know. So what we do is we write the vectors as columns in a matrix. We reduce, and they are linearly independent, means is equivalent to you have a leading one in every column. So every column gets a leading one. By the way, that's the same thing as this. That's the exact same thing as A equals 0, B equals 0, C equals 0, blah, blah, blah is the only solution. So that's how it looks like. This is equivalent to when you have A1 V1 plus dot dot plus AK VK equals to 0, has only A1 equals to 0, A2 equals to 0, all the way down to AK equals to 0 as a solution, as the only solution, has only this as solution. So this is the same thing. I'm just saying how it looks. How do you get this? How do you get A equals 0, B equals 0, C equals 0? You get a leading one in every column. We're going to revisit this when we do the image, the basis of the image space. Row reduce, meaning do the row operation. Leading ones, pivot. Do you call it a leading one, pivot? What do you call it? You remember when you reduce and you get like 1 0 0 0 0 1. Right. You do have matrices. Oh, you haven't done matrices yet? You do have matrices. You have systems of linear equations, right? So it means you get a leading one in every column. If you haven't, if you're not super comfortable with this yet, with this notion yet, then you could always stick to this. That's fine. Oh, Evan. Okay, Evan makes it. Okay, I'm okay. Yeah, so you have done leading ones. Those are I will say more on this later. The notion of leading ones, I will say more about this later. Evan, your comment sometimes escapes me. I forget that part. So I will remember it. So let me give you an example here to see how this works. Your class is at 8:30. So is let's say this vector 1 0 1. Actually, you know what? Let me just make it a bit more interesting than this. So is 1 0 2 1 0 1 2 1 and 2 1 6 3. Is this set linearly independent? So let's just answer this. This is a basic question, and I am certain that they will ask you some form of this question on your midterm. You're going to definitely get a question of, are these vectors linearly independent somehow, somewhere? So might as well do this now. Are these vectors linearly independent? How do we check that they are linearly independent? They're linearly independent if when you write A times the first vector plus B times the second vector plus C times the third vector equals to 0. So you're going to solve this, right? And if the only solution is A equals 0, B equals 0, C equals to 0, then they are linearly independent. If you have other solutions, then they are not linearly independent. Do you at least get this bit? Everybody gets this. So vectors are linearly independent if the only solution to this equation is all the variables are equal to, all the constants equals to 0. Are we okay with this bit? So vectors are linearly independent. So if I put them in an equation, A times the first plus B times the second plus so on and so forth until 0, 0, 0. Now, if the only solution is A equals 0, B equals 0, C equals to 0, then they are linearly independent. If we have other solutions, then they are dependent. So I'm going to even write this again. So if we only get A equals to 0, B equals to 0, and C equals to 0, that means they are independent. If, or else, or whatever, if this is otherwise, meaning we get other solutions, that means they are dependent. Okay, so let's Julia, I don't know what you mean. but I'm guessing that comment wasn't for me. So let's do this. This gives me A plus 2C is equal to 0. B plus C is equal to 0. 2A plus B plus 6C equals to 0. And then A plus B plus 3C equals to 0. Now, how you solve this? I suggest we go to matrices, since we have to do matrices in RREF. There's several ways that we could do this. For example, if you don't want to go to matrices, which I prefer, but let's say you don't, you can say from here that A is equal to minus 2C. From here, you can get B equals to minus C. It's 2B in the third row. You are absolutely right. So when you replace those in here, oh, I am going to show you using matrices for sure, Mark, 100%. So if you replace them in those two equations, you will get 0 equals to 0. So it will be useless. Those two equations will be just, if you replace A by minus 2C and B by minus C in those two equations, you'll get absolutely nothing. So you'll get 0 equals to 0. Which means what? Which means 0, 0, 0 isn't the only solution. Which means that your solution is C can be whatever it wants, and then A would be minus 2C, and B is equal to minus C for any C. Which means that A equals to 0, B equals to 0, and C equals to 0 is not the only solution, which means they are linearly dependent. Okay. Now, if you want to do this using matrices, and I don't mind using this now, because you have matrices in systems, so it would be a good practice. How do we do this using matrices? The first step is we write the augmented matrix. I am explaining now a topic within a topic, so it's kind of a dream within a dream. You're dreaming that you're dreaming. So we write the augmented matrix of this, which basically means this without the A's and B's and C's. So 1A, 0B, 2C equals to 0. 0A, 1B, 1C equals to 0. 2A, 2B, 6C equals to 0. And then A, B, and C equals to 0. Well, it's all linear algebra, but yeah, it's entering sort of the row reduction multiverse if you want. So how do we solve this? Our goal is to work column by column. Please remember this, because later I'm going to say that we talked about it, so we're not re-entering this. So our goal is to work column by column. So you finish working with your first column, then the second column, then the third column, and so on. Now, what do you do when you start working in a column? The first thing, you get the leading one. So in the first column, the leading one should be here. In the second column, the leading one should be here. So you get the first entry that is non-zero, and then you use the one to get zeros. So let's see. So I have the leading one where I want it here. So I need a 0 here, which I have. Then I need a 0 here, and then I need a 0 here. How am I going to achieve 0 here? I'm going to use row operations. What are the row operations? So I'm going to do minus 2 times row 1 added to row 2. That's my new row 2. So basically, I'm doing this. I'm saying to myself, what do I multiply 1 by? So when I add it to 2, it gives me a 0 because I want a 0 over here. One more time. What do I multiply the 1 by? So when I add it to 2, it gives me 0. So 1, row 1 multiplied by what? So when I add it to row 2, I get the 0 that I want right here. And the answer is basically minus 2 because you want to cancel the 2. So minus 2 row 1 plus row 2. I prefer, Evan, if you use your row 1 because your leading one is right there. You could use other rows. I want to keep the 1. I'm not changing the 1. Row 1 doesn't change mine. Row 1 is unchanged. 1, 0, 2, 0. That's unchanged. What's changing is row 2. So you're doing, what's changing is row 3. I apologize. Row 2 doesn't need to change because row 2 is a bunch of zeros anyway. So this is 0, 1, 1, 0. Right. I want to keep the 1. I'm not changing the 1 mark. I am just changing the 2 here. So minus 2 times 1 is minus 2, plus 2 is 0. Minus 2 times 0 is 0, plus 2 is 2. Minus 2 times 2 is minus 4, plus 6 is 2, and that's 0. Now, the other operation is minus 1 times row 1 plus row 4 into row 4. So if I want to cancel this, I'm basically doing minus 1 times row 1, and I'm adding it to row 4. So this would be 0, 1, minus 1 times 2 is just 1, and then that's 0. And I finished working in my first column. This requires practice. This requires plenty of practice so you don't make a mistake doing it. So now I'm going to focus on my second column. For my second column, the leading one should be here because I'm looking at my second row. There's 0. Then the first entry that's not 0 is that one right here. So that's the one. That's what I call the leading one of row 2. Now I want everything else to be 0. So I want a 0 over here, a 0 over here. And if this wasn't 0, then a 0 over here. So what gets me a 0 over here and what gets me a 0 over here? So the operation is minus 2 times row 2 added to row 3. That's my new row 3. And minus 1 times row 3 plus row 4 into row 4. That's my new row 4. That tells me that row 3 is changing, and that tells me that row 4 is changing. Row 1 and row 2 are untouched. So 1, 0, 2, 0, 0, 1, 1, 0. Now, when I do this, you'll notice that these will just disappear. And I'm done. This is what we call our REF. I'm not going to get into more details in this. I want to do matrices a bit later, so I will go through a bit more details of this later. Right now, I want to keep my focus on linear independence in basis. Tristan, what does that mean? So remember, this is the column for A, this is the column for B, and this is the column for C. Okay, this is the leading one. This is the other leading one. There are no leading ones here. Where do I get a leading one, Alexander and Z? If I wanted to get a leading one, I would need a leading one to be here. I can't get a leading one here. So I can't get more leading ones, and therefore I stop. Let me see what the other questions. So since there is no leading one here, there's nothing else for me to do. So I'm going to tell you, you are solving this system, Julia. You take this, you do this, and you're solving it. Look, see here, this row tells me that A plus 2C equals to 0. And this row tells me that B plus C equals to 0, which tells you that A is equal to minus 2C and B is equal to minus C, exactly like the solution I got before. Which means 0, A equals to 0, B equals to 0, and C equals to 0 is not the only solution. Basically, I can pick whatever C I want and I will get a bunch of solutions. Therefore, the vectors are linearly dependent. Julia, these are called the elementary row operations. The elementary row operations these are the operations that you are allowed to use. The elementary row operations that you are allowed to use you can switch two rows, Ri switched with row J. You can switch two rows. You can multiply a row by a non-zero constant. So you can take K times row I into row I. And you can add a multiple of a row to another. So K row I plus row J into row J. Okay, so there's a bunch of questions. Let me read them. What's the point of getting this? So we answered this. Minus row 3 plus row 4. Sorry, the operation is minus row 2. Sorry, I'm sorry for the confusion. I'm using row 2 to cancel row 3 and row 4. Sorry, Matthew. It's row 2 that I'm using. Yes, here C is called a free variable. Because C can be whatever you want, and then A and B will depend on C. Imogen, that's excellent. If we get the matrix in RREF form, does that mean it's linearly independent? No. You need a leading one in every column. So, sorry, just give me a second. I'm going to be right back. Just give me 1 second. Sorry about this. Okay, so Evan, we answered this. How do we know it's linearly independent? Look, Matt, because you can give C any value you want. Let's say, for example, C equals to 1, for example, gives you A equals to -2 and B equals to -1. So this is a solution that where A, B, and C are not 0. And Arya, I believe I answered this. RREF doesn't mean they're linearly independent. This is RREF. I will say more about RREF later. Linearly independent means the only solution is A equals to 0, B equals to 0, and C equals to 0. Yes, but only Arya above leading ones. So this is a leading one, so you get all zeros. This is a leading one, so you get all zeros. But there is no leading one here, so there could be whatever you want. Fair enough? Yes, all the numbers before the leading one should be 0 because, Jason, the definition of leading one is the first non-zero entry in a row. So there's a bunch of zeros, and the first entry that's not 0 is the leading one. Maybe after this, I should just go and do the matrices right away because it seems we're having a little bit of difficulties with this. Okay, so let me show you. Let me show you an example of a system where they are linearly independent. So you can see how that works. So let me give you this example. So let's say we have the polynomials of degree 2 in x. So these are all the polynomials of degree less than or equal to 2 with coefficients in R. So maybe you just put R. Do you put R or you put X? I don't know which notation you use, but let's say P2, all the polynomials of degree less than or equal to 2. Let's take the first polynomial to be 1 plus X, the second polynomial to be X plus X squared, and the third polynomial to be 1 plus X squared. Is F1, F2, F3 linearly independent? So this is a question that I took as a variation of one of the questions on your test. So how do we look at this? There's two ways to look at this. One way to look at this is as vectors like this. So we can say A times F1 plus B times F2 plus C times F3 equals to 0. And they are independent if the only solution we get is A equals 0, B equals to 0, and C equals to 0. And if they're dependent, if I have another solution. That's one way to look at this. The other way to look at this is to transform these into vectors, to make this as sort of to do the equivalent operations in a different space. So we look at this, so we think of P2 like R3, and I will tell you why like R3. Because P2 is all the polynomials A plus Bx plus Cx squared. Meaning you have 1, 2, 3 constants, 3 in R. So R3 is like the vectors A, B, C. So any element in R2, like F1, realistically, it's the vector 1, 1, 0. 1 plus 1x plus 0x squared. x plus x squared is the vector 0, 1, 1. And 1 plus x squared is like the vector 1, 0, 1. So we can think of these as polynomials in P2, or we can think of these as vectors in R3. Those two spaces are basically the same. So one would say A times the vector 1, 1, 0 plus B times the vector 0, 1, 1 plus C times the vector 1, 0, 1 equals to 0, 0, 0. And again, this does not change. This is, in both cases, this is the case. So I'm going to solve this in both ways, right? I'm going to show you the solution to both ways. If we're working number one, then we're going to say A times 1 plus x plus B times x plus x squared. I'm going to show you how this will give you back this. You'll see. Plus C times 1 plus x squared is equal to 0. So that means A plus ax plus bx plus bx squared plus cx squared equals to 0. So the constants are a plus c. The coefficients of x are a plus b. And the coefficients of x squared are b plus c. That's correct, Alex. Now, this is equal to 0 for any x, of course. We can't have it equal to 0 just for some x. That tells me that a plus c must be 0. A plus b must be 0. And b plus c must be 0. And that's the system I'm solving. Okay, I want you to look at this and to look at this and tell me, are they not the same equations? Basically, that's just two starts here. Please take a moment to verify that these are the same equations. Look at the first row, A plus C equals to 0. The second row is A plus B equals to 0. And the third row is, sorry, there's no A, B plus C equals to 0. Do we see how those are exactly the same equation? Okay, now let me solve this for you. 1, 0, 1, 0. 1, 1, 0, 0, 0, 1, 1, 0. Remember how we do this? What would 2x squared? 2x squared would be 0 plus 0x plus 2x squared. So it would be the vector 0, 0, 2. Right, Z? So let's work this out. We have a leading one here. We want a 0 here. So the operation is negative rho 1 added to row 2 into row 2. That's 1, 0, 1, 0. Minus this plus this, minus this plus this, minus this plus this. 0, 1, 1, 0. I got a leading one where I want it to be. I need the 0 over here. So negative row 2 plus row 3 into row 3. Zero, 1, minus 1, 0. Minus this plus this, minus this plus this. Take row 3, multiply it by a half, put it into row 3. 0, 0, 1, 0. Then I got the leading one where I need it to be. I want a 0 over here and a 0 over here. And if I do the operation 1 times row 3 plus row 2 into row 2, and minus row 3 plus row 1 into row 1, I get the final matrix. You see how we got a leading one in every column? Remember what I told you before, my earlier remark is if we get a leading one in every column, that means they're linearly independent. Why is this? Because this is the column for A, this is the column for B, and excuse me, this is the column for C. This tells you that A is equal to 0, this tells you that B is equal to 0, and this tells you that C is equal to 0. Yes, there can, Evan. Look, this is RREF, and there are numbers in the other columns. Don't mix RREF with linear independence. Do you understand what I'm saying? You're done working with this. This is RREF basically means the final matrix you get to. I'm gonna discuss this right now because it's creating less. If you have a leading one, then yes, the columns are zeros. So there are the vectors are here. The vectors are linearly independent. Do we get this? I want to discuss one more topic before I switch to matrices. I don't want to cut this in half. So we've done linear independence, we've done span, we've done the test of linear independence. I want to discuss with you before we switch to other topics, the idea of basis. So what is the basis of a vector space? So vectors v1 up to vk is a basis for v, and the dimension of v is n. We are getting a break very, very shortly. This means that v1 up to vk is a generating set for v, and v1 up to vk is linearly independent. So we get a basis. A basis are vectors that generate the space. They are a generating set and are linearly independent. Now, very, very important. If they are a generating set, that means k must be bigger than or equal to n. If they are linearly independent, that means k is less than or equal to n. And when you combine those, that basically means k is equal to n. So what's the number of vectors in a basis? It's exactly the dimension. This tells me that the dimension of v, this is the number of vectors in a basis of v. Right, and by the way, a basis is not unique. A basis is not unique. Right, you could have several bases for the same space. So, as a summary, as I said, the dimension is the number of vectors in a basis. It is the maximum number of linearly independent vectors in V. So you can't have more than n linearly independent, and this is the least number of vectors required to be a generating set. And again, in this case, it's not guaranteed. Yeah, a basis is not unique. You could have two different bases for the same set. Generating set. Right? Generating set, Andrew? So that means if you want to do you want to use a different word, you can say that these V vectors span V. Would you prefer span V? And Sydney, as shocking as it is, and you don't explore this in APSC 174 enough, you maybe explore it in other courses. You can have two different bases for the same set. A basis is not unique. This is why we call a basis for a vector space, not the basis for a vector space. All right, we are gonna do a lot more about this. So to give you an idea of what is the plan next, the plan next is we're gonna take a small break. Then we're gonna practice this idea. We're gonna practice the idea of basis and generating set and linear independence. And after this, I'm going to go back and I'm going to do matrices. I'm going to do basically system of linear equations and RREF and all those things that, we mentioned here. I want to do them today so everything is clear and we can close the whole the whole loop on this. And then once we do this, we will start with linear transformations, I suppose. K is just, Alex, K is the number of these vectors. And N is the dimension of V. Right, Alex? And the recording usually takes 24 hours. So at some point tomorrow after we end today, so I would say tomorrow around 4-ish, it just takes some time for them to make it work and post it and whatnot, and that's when we get into it. So are we okay up to this point? So let's take our break. This is 50 minutes. Right now it is 2:15. Let us be back at 2:30, 15 minutes to practice some more. There's a good chance that we're gonna not take a second break. There's a good chance that we're gonna go one shot from 2:30 till 4 p.m. so we can, save the break time to maximize the learning. So rest well on this break because I don't think we're going to take another break after it. We're going to go all the way till the end. All right. See you guys in 15 minutes. Hey everyone, here we are. So, as practice to all the concepts that we just learned, let's talk about this problem from 2021, which deals with basis, dimension, and all that. So let's see. We have the C infinite R, which are the functions that are infinitely differentiable. Consider the subspace H, which is spanned by these functions. So H is the span of the two functions f1, f2. And if you remember from the midterm 1 session, anytime we use the word span, the span of any vectors, as soon as you say span, this is a subspace. This is a subspace of C infinity R. As soon as we use the word span of the vector, that would be a subspace. I'm not sure what you mean by what test it is, but you test the subspace. You test that it's closed under addition, it's closed under scalar multiplication, and it contains the zero vector. We did all of that for the midterm 1 session. Sorry, what's here? This is 2021, sorry. So we know that H is a subspace. We need to find a basis for H. So basically, to find a basis for H, let's review what we know about basis. For basis, we need to find a span. We need to find a generating set, which means we need to find the set that generates H. And we need to find that set to be linearly independent. So we need to find the set that's a generating set and linearly independent. Right away, we have for free a generating set. What is a generating set for H? What's a generating set for H? H is the span of F1, F2. That means F1, F2 is a generating set for H, right? Because any element in H is generated by F1 and F2. Anything in H is the span of F1 and F2. That means F1 and F2 generate the entire H. So we get that for free. So if we can show that F1, F2 are linearly independent, so if we can show that F1 and F2 are linearly independent, that means we have our basis. Now, if F1 and F2 would not be linearly independent, then whatever set that's linearly independent, that would be by itself the basis. I'm going to show you this in just a second. So are they linearly independent? What's the test for linear independence? Well, we take A times F1 plus B times F2 is equal to 0. Here we cannot take them as vectors. These are not the polynomials of degree less than or equal to 2, right? These are just any function. So let's just stick the functions here. So A times minus 2 plus 2x minus 3x squared plus b times 1 minus 3x plus 2x squared is equal to 0. So the constants we have minus 2a plus b. The coefficients of x, we have 2a minus 3b. And the coefficients of x squared, we have minus 3a plus 2b. And if this is equal to 0 for all x, that means minus 2a plus b is equal to 0. 2a minus 3b is equal to 0. And minus 3a plus 2b is equal to 0. So we're just gonna check which one, what's the solution to this. This tells us that b is equal to 2a, this one. So if I plug it in here and I plug it in here, I will get A equals to 0. And if I replace it back in there, I will get B equals to 0. You can also use matrices for this if you want, though this is much, much simpler used without matrices. You can, but here it's much, much faster not to use matrices. So you just plug B equals to 2A in, let's say, so you take, if you want me to solve it super formally, let's call this equation 1, equation 2, and equation 3. If you take B equals to 2A and you replace it in equation 2, you're going to get 2A minus 6A is equal to 0. That means A is equal to 0. And if you take B equals to 2A and you replace it in equation 3, that would be minus 3A plus 4A is equal to 0, which also gives you A is equal to 0. So here that both of those tell me that B equals to 0. Therefore, A equals to 0, B equals to 0 is the only solution, which means F1 and F2 are linearly independent. They are linearly independent, and they are a generating set. Therefore, F1, F2 is a basis. Well, you solve a couple of problems, Marth. There's just no definitive way. I mean, if you were to use matrices, it would be minus 2, 1, 2, 3, 2, minus 3, and then minus 3, 2, 0, 0, 0. I mean, you can see right away that there's some computations that need to be done here, but then if you do that, it's a little bit faster. And when I say faster, please don't think like one of them takes 2 days and one of them takes like a minute. One of them takes 2 minutes, one of them takes like 4 minutes. So if you do one method or the other, it's not like, you know, the fate of your exam hangs on it, right? Okay, so what is the dimension of H, ladies and gentlemen? From what we just have done here, what's the dimension of H and why? What is the dimension of H? Evan, you want to think again? Very good, everyone. The dimension of H is 2. Why is the dimension of H is 2? Because there are 2 vectors in the basis. Remember what we said about the dimension of a vector space. Do not forget this. It's the number of vectors in the basis. It's a maximum number of linearly independent vectors. It's the least number. Basically, that's the one that's the most important. The number of vectors in the basis. This is very important. You should not forget. All of this is posted for you. All of the 2019, 2021, and 2022, they gave them to you already and they're solved, so you have them. I gave you 2016 to 2018 posted on the CourseCram website with full solutions, obviously, and my notes will be posted for you tomorrow at 4 p.m. So basically, you just have to pay attention. Do you get this? I also wanted to say a comment that I faced not in a Queen's session, but at a different university. At the end of the session, somebody sent me an email saying, yeah, whatever, the session was awesome, but you really should do more theory. You should spend more time explaining the theory and whatnot. And I answered this person, like, this is a prep session, right? If I'm going to take the time to explain the theory like they do in class, we won't finish. Like, we will need all the time you've done in class. So, right, like this is a prep session. My focus is that you ace your test, and the way that I can get to this is by helping you solve problems, right? So, and when you solve problems, then you'll be able to understand the theory more, right? So the solution is not me spending more time on theory. The solution is we do the theory, then we practice it several times so we could, you know, understand the theory. I love you too, everyone. Again, this wasn't at Queens, this was at a different university. Anyway, I'm just saying this, like, so you know, look, my goal is that you ace the test. Like, if I had a magic button that I press and you ace the test, I would press it, right? And then if you want to learn the theory in depth, then once you ace the test too, then take a couple of days to, you know, read about the theory and watch videos and whatever, right? The goal is the acing of the test right now. So determine with proof whether these vectors are linearly independent. So let's go get F1 and F2 so we can have all of these together. So how do we check linear independence here? Thank you, Juan. So we know the test of linear independence. These vectors are linearly independent. If I put them as AF1 plus BF2 plus CF3, and I make this equal to 0, and they are linearly independent I can write right now, independent, that means that the only solution we get is A equals to 0, B equals to 0, and C equals to 0 is the only solution. I must have written this 7 times by now, but it's worth it because you really need to remember. Thank you, Austin. So let's take a moment to write this down. You know what? Maybe take 30 seconds and set this up. Take 30 seconds to set this up. You may not have time to solve all of it in 30 seconds, but take a moment to set this up, and then I have the next problem ready and going for you. So this is 2021, at least I think it's 2021. So for the constants, we have minus 2a plus b minus 3c. For the coefficients of x, we have 2a minus 3b plus c. For the x squared, we have minus 3a plus 2b minus 4c. And if we wanted this to be equal to 0 for all x, that means we're going to get the equations minus 2a plus b plus 3c equals to 0, 2a minus 3b plus c equals to 0, and minus 3a plus 2b minus 4c equals to 0. And here we kind of have to well, it's asking if they're linearly independent, so that means you're going to get a solution that's not just A0, B0, and C0, right? So you will get that if you get 0, 0, 0 as the only solution, it's independent. If not, then they are dependent. And really, this way we have to use matrices. This is way too annoying to solve otherwise. What I do usually is I try to find, I tried to, say that again, is the first equation plus 3c or minus 3c? It's minus 3c. Yeah, so minus 3c. Here we go. So I usually try and find an obvious connection between them, so I can say right away like they are dependent. So let's say if you can see right away that F3 is F2 plus F1, then they are dependent. I tried to look for something obvious. I couldn't see it. I don't know if you can. Like I can't see one that's obvious. So minus 2, 1, minus 3, 2, minus 3, 1, and then minus 3, 2, minus 4, 0, 0, 0. And we reduce this and we check if 0, 0, 0 is the only solution. Now, in the interest of practicing, I'm going to solve this, but this will probably be the last one that I do in details, like a full solution. So I need a 1 over here. How am I going to get a 1 over here? I could do minus row 3 plus row 1 into row 1. That's a complicated operation. People don't always see it. Most people will say row 1 divided by minus 2. You know what? I'm going to do what most people would do. I won't get too smart for myself. So R1 divided by minus 2 into R1. Let's do it how most people would do it. And then, so this would be like this. So this is 2 minus 3 minus 3, 2, 1 minus 4. Now I need to get a 0 over here and a 0 over here. So minus 2 times row 1 added to row 2, that's my new row 2. 3 times row 1 added to row 3, that's my new row 3. This takes a lot of practice so you don't make mistakes. And I'm the king of mistakes in this because I don't practice nearly enough because I just use software. So minus 2 this plus this. Minus 2 this plus this, minus 2 this plus this, 3 this plus this, 3 this plus this, 3 this, that's 9 halves plus this. And we clearly see that they're going to be dependent because those two rows are going to cancel each other. I mean, maybe you can't see it right now, but you'll see it in a second. Row 2 divided by minus 2, that's my new row 2. So that'll give you 1s here. Now when you do the operation, minus 1/2 row 2 into, plus row 3 into row 3. You know, I'm also going to do a 1/2 row 2 plus row 1 into row 1, even though this is not really needed here. But I'm going to do it because I have a thing that I want to show you. So I have the leading one. I am using it to create a 0 over here and a 0 over here. That's going to give me 0, 0, 0. So because we killed off a row, you know that they are going to be dependent because we don't get a leading one in every row. So a 1/2 this plus this, a 1/2 this plus this, and here we go. So what does that tell me? This row tells me, remember, these are the rows for the A, B, C's. This row tells me that B plus C is 0. So B is minus C. And this row tells me that A plus 2C is 0. That means A is equal to minus 2C. So what we call C is our free variable. And depending on C, we can get A and B. So these vectors F1, F2, F3 are dependent. So F1, F2, F3 are dependent. Okay, I want to take this a step further, guys. How are they connected? How are they connected? Like, what's the link between F1, F2, and F3? How are they connected? What's the relation connecting F1, F2, and F3? We said that they're dependent. So what's the relation between them? How do they connect? This is why I did this. So please pay attention to this note. We know that A is equal to minus 2C and B is equal to minus C. So say C equals to 1. And if you don't like 1, then pick any other number you want. then A is equal to -2 and B is equal to -1. That means -2f1 minus f2 plus f3 equals to 0, right? Because isn't it af1 plus bf2 plus cf3 equals to 0? And therefore you can solve for whichever one you want. So which one do you want to solve for? Let's say f2 or f3. You can say that f3 is 2f1 plus f2. And is it true? f3 is 2f1 plus f2. 2f1 plus f2, where you go, 2f1 plus f2, it works out. So f3 is 2f1 plus f2. So we know that f3 is a linear combination of f1 and f2. You could have solved for anyone, right? You could have solved for whichever one of them in terms of the others. Do I make sense? This is an extra step that wasn't needed. Okay, I want to do one more problem. Actually, I want to do more problems, but there was number 4. I love this one. This was also 2021. But it gives us another sort of type of problem that we want to deal with. So you know, this is 2020. Are we ready for this? So this is a little bit harder. So suppose that W is a subspace. So W is a subspace of R3. What's the dimension of R3? Dimension of R3 is 3. Very good. Now, W is the subspace of R3 that's defined like this. So we want a basis for W. To get a basis for W, we need to just do anything with W. You really need to understand this. Just like when we did in midterm 1, I told you to prove W is a subspace, you needed to understand what W is. To find the basis for W, to do whatever with W, you really need to understand, like, okay, what's W? Like, look at W, not just like, you know, go in depth. What does W tell me, guys? It's all the vectors x, y, z, such that x is y, and z is minus 2y. So really, W is the set of the vectors, is the set of vectors that are x is equal to y, so y, y, and z is minus 2y for any y and r. You see what I did just there? I'm going to show you a slightly harder example than this in just a second. So basically, W is y times the vector 1, minus 1, 2, where y belongs to r. So can you tell me what W is in a more nicer way? Who can give me W in a nicer way? Of course, we haven't done transformations yet, so let me just block this out. We will do the transformation bit later. Yeah, so all this part we will do later because this is linear transformations. Right now we're just focusing on basis. I'm 100% sure you know this. And when I tell you, you're going to be, I knew this. How could I write W in a nicer way? W is y times this vector for all the y's that are in R. So can't I say that W is just the span of this vector? It's all the copies of this vector, right? So basically, they're asking us to find the basis for W. Well, hello, basis, right? I mean, clearly, you can say that 1, 1 minus 2 is a generating set, clearly, because W is the span of this. Also, the set 1, 1 minus 2 is linearly independent because it's just one vector. What is it going to be dependent on? Therefore, the basis, a basis for a W is just the vector 1, 1 minus 2. Who can tell me what the dimension of W is? Exactly the dimension of W is 1. Are you ready for a slightly harder problem? I'm ready for a slightly harder problem. So this was a kind of a, if you knew how to do this, if you knew how to read W, then this problem would have been very, very straightforward. Here's a slightly harder version of the same type of problem. So let's say we have W, which is a subspace of R3, same thing, but W is all the vectors X, Y, Z, such that X plus Y, X plus 2Y, whatever, minus Z is equal to 0. Absolutely. So the that's a good question, Z. The dimension of W is less than or equal to the dimension of the space it lives in, which is R3. So the dimension of W could be 0 if it's just a 0 vector, or 1 or 2 or 3. And if W is a subspace, SS is a subspace of R3, and the dimension of W is equal to 3. So if it's a subspace of R3 with dimension 3, then W is the full space, then W is R3. Yes? Okay, guys, so here's the same question. Give me a basis for W. Can I give you 30 seconds to think about this? So when we look at this, we realize that really W is the set such that Z is X plus 2Y. So W is all the vectors that are X, Y, and the last component is X plus 2Y. Right? Where X, Y, Z, so X, Y belongs to R. So how can I write this in a way that reveals the generating set and reveals the basis, right? Look, I can write W as, and if it's the first time you see this, then it's like, mind-blowing. But after 2 examples of this, you'll realize it's really not that big of a deal. So it's the vectors with X plus the vectors with Y's, where X, Y belongs to R. And now you can see it, can't you? This is X times the vector 1, 0, 1 plus Y times the vector 0, 1, 2. So who can write W in a more, nice way, in a more sort of elegant way? W is what, ladies and gentlemen? W is the span of the vectors 1, 0, 1 and 0, 1, 2. So if you want a basis, the basis presents itself to you right away. So the set 1, 0, 1, 0, 1, 2 is clearly a generating set for W. I say clearly because W is the span of those. So those are basically creating W. And the vector 1, 0, 1 and the vector 0, 1, 2, they are not parallel. So they are linearly independent. And this only applies if there's just two vectors. You remember we talked about this. Therefore, a basis for W would just be this, which means the dimension of W is equal to 2. Are we okay with this? Using this method is generally, yeah. If you use this method, then it would almost always be linearly independent. You're right. I can do one more example, not a problem. So let's take W. X, Y, Z, such that Y is equal to 2X. And then, of course, X, Y, Z belongs to R. So can you get me a basis for W? It's a generating set. If any element in W, you can generate it using these two. Right, Matthew? Generating set, meaning any vector in W is a linear combination of those. But that comes to us for free by saying W is the span, right? W is a number times this vector plus a number times this vector. So clearly any element in W is created using these two vectors. Is it clear? Thank you for asking. Okay, let's do this quickly. Can you get me a basis for W? Now you can do it in 30 seconds. Because now you've seen it a couple of times. Now you can do it in 30 seconds, no problem. So how do I write W? It's all the vectors where Y equals to 2X. It doesn't have to be the smallest, Joseph. It's a combination of vectors that can generate the entire space. That's the idea of generating set. It doesn't have to be the smallest. The basis would be the smallest combination of vectors that can generate the space, and thus they are linearly independent. Right? In a generating set, remember when we spoke about generating sets super early on, we said that if 1001 is a generating set for R2, then 1001 with any bunch of vectors would also be a general set, a generating set, because those two vectors would create R2 and the rest of the vectors can just sit there and sing songs. Right? So it's not the smallest, it's just a set of vectors that would generate the whole space. No problem. Okay, so how do I write W? Is the y equals to 2x. So this is x, 2x, z, where x and z belong to R. So we can break it up into two vectors. That would be the vector x times 1, 2, 0, plus z times the vector 0, 0, 1, where x and z belongs to R. And therefore, W is the span of the vector 1, 2, 0, 0, 0, 1. And, like the same example, that would be, this is the basis. Yes? So the dimension of W is equal to 2. Okay, I'm going to ask you a slightly, not harder, but a different type, a more like combinatorial type, like something that needs you to do some work. Here's a question. Show that this is a show that 1, 2, 2, 3 is a generating set for R2. No, Z could be anything, Evan, right? Because there is no requirement for Z, that literally means Z could be anything. So y equals to 2x, and what's not said is here that Z, look, Z can be any element of R. So that's why Z gets a whole component for itself. Right? Okay, so how do I show that 1, 2, and 2, 3 is a generating set for R2? Okay, there's a long way and there's a short way. I'm gonna do both, but I don't like the long way. So this is the long way. I don't like it, and I don't think it's very, very, interesting. But I'm gonna do the long way and the easy way. Why am I doing the long way? Because sometimes there is no other way. In this case, there is. So this is a generating set for R2. That means any xy in R2 can be written as xy equals to a times 1, 2 plus b times 2, 3. Do you follow up to this point? Again, for some a and b. Yes? Up to this point, are we clear? So it's a generating set of R2. If any xy in R2 can be written as a times 1, 2 plus b times 2, 3 for some ab. What does this really mean? This means that this equation has a solution a, b for any xy. So you give me the xy, there will be a solution. Guaranteed there's a solution for any xy. Are we clear up to this point? So guaranteed there's a solution for any xy, meaning I can solve for AB in terms of x and y. So that means I can find what A is and what B is in terms of xy, so that whatever the xy are, I get a solution AB. So let's do this. Let's solve for A and B in terms of x and y. So A plus 2B is supposed to be x, and 2A plus 3B is supposed to be y. Now, here, if it's 2 by 2, I recommend you just solve it and, the old-fashioned ways, the kind of high school methods. So for example, here you can say that A is equal to X minus 2B. You replace it here. So 2 times X minus 2B plus 3B is Y. So 2X minus 4B plus 3B is equal to Y. So minus B is Y minus 2X. So B is equal to 2X minus 1. Notice I am solving for A and B in terms of XY. So when you replace that back here, you're going to get A is equal to X minus 2X minus Y. So X minus 4X is minus 3X plus 2. So I am able to solve for A and B in terms of XY. Okay, what does this mean? Furthermore, it means you give me any vector XY, then I am able to write this vector as minus 3X plus 2Y times the vector 1, 2 plus 2X minus Y times the vector 2, 3 for any XY. So whatever the XY is, I am able to write it as a combination of this and this. And thus, this tells me that the vectors 1, 2, and 2, 3 are a generating set for R2. So it's a little bit annoying, but it's a method, it works. What's the shorter way? The shorter way relies on a theorem that I don't know if they gave it to you or not. That's why I did the long way. The shorter way says that if, so in Rn, if n vectors are linearly independent, then that's equivalent to they are if they are linearly independent, then they are a basis for Rn. Okay, let's not do this. Let's say if we have V such that the dimension of V is n, so for any vector space of dimension n, if n vectors are linearly independent, then they are a basis, which means you get automatically that they are a generating set. And if n vectors are a generating set, then automatically they form a basis, which means you get by automatic linear independence. Again, what's the key here? That you have the same number of vectors as the dimension. So if you have the same number of vectors as the dimension gives you the number of vectors in the basis. So if they're linearly independent, then they're just a basis, because that tells you that the basis has n vectors. So if you found n linearly independent, then they are a basis. And if you find n that are a generating set, then they are automatically a basis. So if you get the same number, if you have the same number of vectors as the dimension, then generating set and linear independence would become kind of the same idea. So here you have the vector 1, 2, and the vector 2, 3. They are not parallel. So these are vectors that are not parallel. Therefore, they are linearly independent. And because there are two vectors in R2, which is again the 2 and the 2, that means they form a basis. That means they are a generating set. They form a basis for R2. And obviously, if they're a basis, so also a generating set. Again, I don't know if they gave you this bit right here, but that's a very useful bit when the number of vectors matches the dimension. When the number of vectors matches the dimension, then all sorts of fantastic things happen. Okay, now before I move on to another topic, I want to discuss the coordinates with respect to a basis. So coordinates with respect to a basis. And then let me read your comments first. What does the text in the bracket mean? This one? That means if it's a basis, then it's also a generating set. Right? With generating set, the red text. Like automatically a generating set. If it's a basis, then it's automatically a generating set. And if it's a basis, then it's automatically linearly independent. No problem, Angel. And Evan, what would an example with this theorem look like using the bottom line of the theorem? Like if they are a generating set, like if you show that something is a generating set, that means they're automatically a basis. Just like here. I mean, here you didn't know that the dimension is 2, right? But then you showed that this is the span of these two vectors. If you knew that the dimension of W is 2, that means you could have said right away it's a basis. Usually we go for linear. Usually this is more, the first line is more used than the second line because it's easier to show that it's a linearly independent vector. This always happens, Sydney. This is what I'm saying. If you have n vectors and are linearly independent, then they are automatically a basis. If they're not linearly independent, then clearly they are not a basis. Right? I'm not sure I'm like being clear here. So if you have a vector space of dimension n, so you know the dimension is n. If you find n linearly independent vectors, then they're automatically a basis. There is no scenario where this doesn't happen. If they are not independent, then they're not a basis, sure. Because if they're not independent, automatically they are not a basis. Because for a basis, you require generating set and independence. Am I more clear? You haven't said anything, Sydney. Oh, the shorter way doesn't always work because like let's say you have 3 vectors. So let's say here, what this problem is saying is that show that these 2 vectors are a generating set. Because you have 2 vectors and you're looking for a generating set of R2, you can use the shorter way. If they asked you, show that 1, 2, 2, 3, and 1, 1 is a generating set, then this clearly is not independent. So you can't use the shorter way, you have to use the long way. Do you understand what I'm saying? Like here you can't use the theorem that these are linearly independent because they're not. So you really have to go through the whole way and solve for ABC in terms of X, Y, and Z. You actually, that was a very good question. Okay, so what are a coordinates with respect to a basis? So let's say we have, I don't know, B1 and B2 is a basis for W, let's say. So the element X in W has coordinates AB with respect to W. When we put a W there, that means it's with respect to W. This means that X is equal to A B1. Oh, that's an ugly. So let's make these W1, W2. There's too many B's. So W1 is a basis, and X in W has coordinates with respect to the basis W. Sorry, with respect. Hold on, I'm messing up my names. So let's call like weird looking B is a basis for W. X is in W, and it has coordinates AB with respect to the basis B. So we're not saying it has coordinates AB. No, it has coordinates AB with respect to this basis. So the coordinates are with respect to that basis. What does that mean? It means that you can write X as AW1 plus BW2. So the A is with respect to W1, and the B is with respect to W2. Let me give you an example. So let's say you have, let's say W is equal to the span, or let's make it as an easier one. So let's take 1, 0, 1 and 0, 1, 1. Let's say this is a basis for W. What are the coordinates of this vector with respect to, let's call this funny looking to B. So this is a basis for W, meaning those two vectors which are linearly independent create all of W. By the way, in a different way, we can technically say because they are linearly independent, we really can say that W is the span of 1, 0, 1 and 0, 1, 1. No problem. So what are the coordinates of this vector? This vector is in W. What are the coordinates of this vector with respect to this basis? Meaning, what does it mean? Coordinates with respect to the basis. It means you want to write -2, -1, -2, 2, -3, -1. You want to write it as A times this vector plus B times this vector. So that means if we call this vector, whatever you want to call this vector V, so you want to say that V has coordinates A, B. Sometimes they like to write it like this. Sometimes they like to write it like this. I don't know what your teacher prefers. With respect to W, this means that V is A with 101 and V times 011. It means this is how we write V in the basis W. Do you follow what I'm saying? And it's nothing complicated. It's a system of linear equations. So A plus 0B is equal to 2. B plus 0A is minus 3, and A plus B equals to minus 1, which gives you the solution A equals to 2, B equals to minus 3. So V is the vector 2 minus 3 with respect to the basis W. Again, one more time, this means that V is equal to twice the first vector in the basis minus 3 times the second vector in the basis. This is what we refer to as the coordinates with respect to a basis. That's the idea of coordinates with respect to a basis. Right? Okay, I want to do something theoretical. Let's look at the 2020 midterm 2, and I want to look at question 3. This is a little bit of a theoretical question. I want to go over this with you. So let's pick parts A and B, let's say. Determine whether or not justify your answer. So let's pick A and B. Is that the gradient? No, that's just V. You're thinking too much. 172, Alexander. No, we have no gradients in this course. Gradients are for 172. By the way, nobody told me, how was the midterm of 172? Did you do okay? Was it hard? Was it easy? So really, no one mentioned anything. 63 average, it's not so bad. Thank you, Alexander. This is 2020. Awesome. Okay, kind of what was expected. This is what we love about Queens. We kind of expect things. So let's see, let's do this. This is a theoretical. Well, you don't have 2020? Ruth? Well, I seem to have 2020. Then who sent me 2020? I have 2020. Well, good for you. You don't have 2020 and I'm giving you 2020. Isn't that awesome? So let V be a vector space of dimension n. So the dimension of V is n. Determine whether or not each of the following statements is true. I really am just a reflection of you guys. So you help me, I help you, the world is a better place. So let V be a vector space of dimension n, and then they're telling us that if this is a generating set, then n is less than or equal to p. I don't like it this way. I prefer it to say p is bigger than or equal to n. Is this true or false? True or false, ladies and gentlemen? This is definitely true, right? This is the first thing I told you about a generating set, because what's a short explanation to this? the dimension of V is equal to n. That means you have n vectors in a basis. So that means you need at least, so you have n vectors in the generating set. If you add more vectors, so you have at least n vectors in a generating set, and therefore if you have a generating set, then P is bigger than or equal to n. It means the dimension is n, so the basis has n vectors. So if you want to get a generating set, you need at least n vectors in there. You need n linearly independent vectors. Okay, so part B, we're saying that if we have a linearly independent set, then n is bigger than or equal to q. I prefer saying q is less than or equal to n. I like to look at it that way. True or false? Evan, I'm going to give you a second chance. And this is definitely true. If we know that this is a linearly independent set, right? So we know that the dimension of V is n. That means we have a maximum of n linearly independent vectors. So if we have q linearly independent, q is the number of those vectors, Mark. Look, q is the number of those vectors. So if we have q linearly independent vectors, that means q must be less than or equal to n, because we can have the maximum number of linearly independent vectors is n. I also want to do C. True or false? There is a generating set for V with n plus 1 elements. Remember, all we know about V is the dimension of V is equal to n. So there is a generating set for V that has n plus 1 elements. True or false? Like literally true, right? Like this is the question that again, Q, Johnny, is the number of those vectors. This is Q. Right? It's the number of the vectors in that set. So is there a generating set? Is there a generating set that has n plus 1 elements? Well, yeah, there's a generating set for n, n plus 1, n plus 2, n plus 3. You could just generating set is, as we said, it's very, very loose, because let's say you have V1 all the way up to Vn is a basis, right? Because the dimension is n, that means there's n vectors in the basis. Then just take V1 up to Vn and put whatever you want there. Put whatever vector you want there. So W for any W in V is a generating set for V. Right? I mean, because any vector in V can be written as, remember I did this with you before, A1 V1 plus all the way till AN Vn and then 0 W. Like you don't even need W. Remember, if these vectors can create the entire V, then these vectors with this vector can create the entire space V, because this vector will just realistically not be needed. You just always put it 0. Now, this vector, by the way, this would be not linearly independent, right? Right? This is not linearly independent because n is the maximum number of vectors that are linearly independent. So when you add 1 to the mix, it no longer is linearly independent. Right? If you have a set of vectors that are linearly independent, then you can take out as many as you want and they'll stay linearly independent. But you cannot add 1 to the mix. Which part? All of it? ABC, Sydney? Sure, let's go through it again. So we're saying that if the dimension of V is n, and we have P vectors, well, there are P vectors that are a generating set. So what can we say about P and n? Well, if this is a generating set, right? We know that P must be bigger than or equal to n. Why? Because n is the number of vectors in the basis. So you need at least n vectors to generate V. So if you have a generating set, that means you have a set that generates V. So P is bigger than or equal to n, because you need at least n vectors in a generating set. Why is that? Because you have n vectors in the basis, and the basis are the vectors that are linearly independent, and they are a generating set. The second one says that if you have Q vectors that are linearly independent, then Q is less than or equal to n, and that's true. Why? Because the dimension of V is n, and what's the definition of dimension? Definition of dimension is the maximum number of linearly independent vectors. So the maximum number of linearly independent vectors is n. So if you have a bunch of linearly independent vectors, that means their number will be less than or equal to n, because the maximum number of linearly independent vectors is n. So the maximum thing that Q could be is n. And finally, there is a generating set with n plus 1 elements, and we agreed that this is true, because if V1 up to Vn is a basis, that means a basis, again, it's a generating set and it's linearly independent. So if this is already a generating set, then just put any vector you want in it. It will stay a generating set, because if these vectors can create the entire space, then these vectors with one extra vector will also generate the space. Like you could just always say plus 0w. Whatever vector in the space can be written like this, because V1 up to Vn is a basis, right? Because V1 up to Vn is a basis. And you could just always add 0w. In fact, this one could be for any number here bigger than or equal to n. You can have any generating set of size bigger than or equal to n you want. So plus 1, plus 2, plus 3, plus 10,000. It doesn't really matter. Okay, I want to add a quick note before I switch to another topic. So if you have vectors V1 up to Vn that are linearly independent, that means any subset is also linearly independent. So we're saying none of these vectors, because the dimension is n, Isaac, right? So we're saying This is a basis because the dimension is n. They gave us this right here. So if we have n vectors that are linearly independent, then any subset of those vectors is also linearly independent because none of those is a combination of the others. Then, if you take a smaller set, there's still not a combination of others. And if you have V1 up to Vn is linearly dependent, then any set containing V1 up to Vn is dependent. Like if you keep adding vectors in here, you're not going to make them magically independent because these vectors already depend on each other. So if you put in more vectors in the mix, they're going to stay dependent on each other. So the more vectors you add, the more dependency there is, right? So when you add vectors, when you make the set of linearly dependent vectors bigger, it's going to stay dependent. And when you have a set that's linearly independent and you take out vectors from it, it's going to stay independent because none of these vectors are depending on each other. So the less vectors you have, the less dependency you have. Now, if you add vectors to here, then you might lose independence. So you got to be careful. And if you take out vectors from here, then you might achieve independence, but we don't know. We have to check. Nothing is guaranteed. Like we have to check every single time. If I may, and I'm going to write it in a slightly different way. So if we have W inside V inside U, so if V is independent, that means W is independent. And if V is dependent, that means W is dependent. Like if you go smaller than independent, you stay independent. If you go bigger than dependent, you stay dependent. This is the same thing as I just said here. In case they throw that at you, you got this. All right. And now I would like to switch to, couldn't W be, yeah, but sorry, I'm saying, sorry, U is dependent. I'm sorry, thank you for catching that up. I meant U. If you go bigger than V, then it stays dependent. Thank you for catching that. We don't know here, we don't know about U, and here we don't know about W. So what we can say is this: we can't say anything about U in the top one and W in the second. All right, so now let's talk about matrices. Let's talk about systems of linear equations. Let's talk about RREF. We mentioned a lot of these topics already. Hannah, it's fixed now, right? Like now it's 100% correct. If this is dependent, then anything bigger is dependent. If this is independent, then anything smaller is independent. Okay, so basic ideas. By the way, can we just maybe go like 10 minutes extra today so we can finish a couple of things before tomorrow, so we're not strapped for tomorrow? Right, just I'll try not to, but maybe 5-10 minutes extra so we don't yeah, we're gonna talk about this out. That's what's coming. Reduced row echelon form. So we know that a matrix is a box of numbers. We're not gonna re-explain what a matrix is. The matrix has size m by n, meaning m is the number of rows, n is the number of columns. We know that when we reduce a matrix, so when we reduce a matrix, that just means what's called the Gauss-Jordan elimination, which we did several times now. I will remind you what this is. So this is reducing the matrix using elementary row operations. These are the operations that we are allowed to apply to a matrix, elementary row operation. From now on, I'm going to refer to those two as EROs. Remember what they are? We talked about them. We are allowed to switch two rows. We are allowed to multiply a row by a non-zero constant. And we are allowed to add a multiple of a row to another. So these are the operations that we apply to a matrix to reduce it, or on a system to solve it. Finally, let's get to this plane. What is reduced row? Sorry, what is row echelon form for? What's row echelon form? And then after that, what is reduced row echelon form? Just allow me to copy them. I don't want to. So I wrote them in the booklet so nicely, so I'm just going to use my booklet. All right, so here we go. Row echelon form is this. So all the zero rows are at the bottom. So when you reduce a matrix, when you reach a point where all the zero rows are at the bottom, and the first non-zero entry on each non-zero row is to the left block, meaning the pivots, so the first non-zero entry, that's what we usually call a pivot or leading one. If it's not a one, then you tend to call it a pivot, but we always make it a one. This line 2 says that the leading ones go like this. Like this. They don't go like this, they go like this. So, for example, this yeah. This is REF, reduced row echelon form. Meaning, if you have zero rows, they are at the bottom, and every row, the first entry in it that's not a zero is our nice one, the leading one that we call, and the leading ones go from left to right, meaning the leading ones don't just jump around. So for example, this wouldn't be REF. So this is not row echelon form. So it doesn't, because the first entry that's not zero in this row is this. The first entry that's not zero in this row is this. That's illegal. Now, what is that super coveted reduced row echelon form, which everybody was asking me about? This is reduced echelon form. This is what we aim for when we are reducing a matrix, or when we are solving a system, or this is the end result. This is the matrix where we stop. All the zero rows must be at the bottom. Technically, they could be any number. It depends on the teacher, to be honest, Evan. Some teachers allow any numbers. Some teachers insist that it's a 1. Like in my classes, I insist they are 1s. Some teachers, sometimes they say they could be anything. So to be honest, I don't know what your teacher chose, but I mean, some teachers accept this as REF. I don't know if your teacher accepts that or not. Some teachers accept this as REF because those are pivots and the pivots go left to right. Do you know if they accept this or not? Again, in REF, not RREF. RREF, everybody agrees on they should be 1. So I'm going to say here, check to see if your teachers accept this. Of course, none of it matters. A pivot is a leading one that's not a 1. Like, you know how this is supposed to be a 1? So if it's not a 1, if it's technically a 2, then then that's what you call a pivot. A leading one that's not a leading one. Let's just, you don't seem to have seen any leading ones. So let's any pivot. So let's just stick to leading ones. Okay, so let's just stick to leading one. You don't seem to have seen the notion of a pivot. Okay, but let's also focus on reduced row echelon form because that's the one that gets asked mostly. So all 0 rows are at the bottom. When you have an entry that's not 0 in a row, the first one of those must be a 1. That's the leading one. So when you go through a row, the first entry that's not 0 must be a 1. The leading ones go from left to right. And above and below leading ones, all entries are 0. That's not REF because the leading ones don't go left to right, Austin. So this one, I'm going to write it here. 1, 2, 3, 1, 4, 5, 0, 0, 0. This is not row echelon form because there's a leading one and that cannot be there. Leading ones have to go left to right. So here, this can't be a 1. Right? See this, you must have a 0 here and then the next leading one should be here. This is where the next leading one should be. It has to be 0, of course, because if this is a leading one, Austin, right, then that's the first non-zero entry. That means all the entries that came before it should be 0. Right? If it's a leading one, then it's the first non-zero entry. That means all the entries before it are 0. So reduced row echelon form, that's when you have a bunch of leading ones and above and below the leading ones are 0. And remember, we talked about a strategy that we work on. So we work column by column. For the strategy to get to RREF is we work column by column. I already wrote this before, I'm writing it again. We first get the 1, and then we use the 1 to get 0. Okay, and since you don't have 2020, I'm gonna give you the question that they asked in 2020, which is this. Give the RREF of this. So this is from 2020. We want to put this in RREF. So we're going to start by switching row 1 and row 2. I'm really not in the mood of dividing by 3. So if I can switch rows, that's an easier way of getting a 1. So 1, 3, 5, 0, 3, 1, 7, 8, 0, 5, 5, negative 5. The difference is this. In fact, the difference is this. Above the leading ones, all entries are 0. This is what makes it RREF, that above the leading ones, all the entries are 0. This is the determining factor for our REF, because REF above the leading ones don't have to be 0. REF just forces under the leading ones to be 0. Oh, thanks, Mark. So RREF is when you have also, you add to the REF the fact that it's above the leading ones, all the entries are 0. Okay, so we're gonna work on this. We're gonna work column by column. So my focus is working with the first column. I got the leading one where I need it to be. Now I want a 0 here and a 0 here. So minus 3 times row 1 added to row 2 replaces my row 2. So that's going to be 1, 3, 5, 0. Minus 3 this plus this, minus 3 this plus this, minus 3 this plus this. And then 0, 5, 5, negative 5. So I finished working in my first column. Now I'm focusing on my second column, and in my second column, my leading one should be here. So it's not a state secret that I should do row 2 divided by minus 8 into row 2. This gives me 1, 3, 5, 0. 0, 1, 1, negative 8, 0, 5, 5, minus 5. So I got the leading one where I need it to be. Now I need a 0 here and a 0 here. It's a very, it's not, it's actually minus 1. As I said, I don't practice this enough, so I make tons of small typos. You should do like I say, not do like I do. I really just solve this by hand when I'm teaching. When I am not teaching, I'm on softwares all the time. I'd like to think I've paid my dues and I'm allowed software. So I really just solve it like this only when I'm teaching. So minus 3 row 2 plus row 1 into row 1, and minus 5 row 2 plus row 3 into row 3. So this row isn't changed. So minus 3 this plus this, minus 3 this plus this, minus 3 this plus this. And that's just going to be a bunch of zeros. And I'm done. This is RRE. Now, what I want to do with you tomorrow, so we managed to finish on time. There was no stress. What I want to do with you tomorrow That's the plan. We're gonna learn how to solve systems of linear equations with parameters. So that's what I'm starting with. And if we go back to the list of topics that we set out to do, tomorrow, what we did RREF, we did row reduction. We just need to solve systems of linear equations with parameters. We did linear dependence. We did basis. We did coordinates with respect to a basis. We did dimensions of a vector space. So tomorrow I'm going to discuss with you how to solve a system of linear equations. I'm going to discuss linear transformations, the image of the kernel, blah, blah, blah. So everything that has to do basically with linear transformations. So tomorrow, the topics are to solve and then transformations with all that it comes with. So image, kernel, matrix, linear, blah, blah, blah. Aaron, where are your leading ones? This is my leading one. Above and below it all are zeros. This is my leading one. Above and below it are zeros, and I don't have leading ones here. So above and below all the leading ones, not all the ones, right? This is not a leading one. This is not a leading one. I would say show your steps. I don't know. That's a good question, Matthew. Matthew is saying, do we need to show our steps? I would, but I don't know. No, a leading one is a leading one. So that one, if that's a -1, then that's not a leading one. Right? And it's called like a leading one. So it's the first non-zero entry. So when you're going through this row, the first entry that's not zero is 1. When you're going through this row, the first entry that's not zero is 1. Right? So those are not leading ones. And it has to be a 1, not a -1. Any other questions? And we have our plan set for tomorrow. All right, so thank you very much. Head office, thank you very much. And I shall see you tomorrow at 1 p.m. If you have any questions, if you have any comments, if you have anything at all, you could always email me. And see you tomorrow. Thanks, everyone. Bye.
Record